welcome to this session. This session now we introduce the appetizers and eigenvalues and eigenvectors. So for the given matrices, show that the stated vectors are eigenvectors and what are, and find their corresponding eigenvalues. So they are this part A and this part B of the problem. Now, to show that a given vector is an eigenvector to a matrix, you have to show that the eigenvector eigenvalue equation we gave in one on the introduction is satisfied. So solution. A vector X is an eigenvector to a square matrix, to an n by n matrix, A, if and only if A times this vector X is equals to lambda X, where lambda is the eigenvalue. So that's what we must confirm. So in the first case, we have the matrix A is given by 2, 0, 0, -1. Let's state now x1. So x1 is given by 1, 0. So we show that if we take A, multiply by this x1, then it's the same as lambda times the same x1 vector. Now let's do the multiplication and see the value of lambda. So A x1 is 2, 0, 0, -1, and this is 1, 0. So at this point, it's assumed that you know how to multiply matrices. So it's row by column. So we'll have 2 times 1 plus 0 times 0, row, column. And then here we have 0 times 1 plus -1 times 0, row, column. So this will be 2 times 1 is 2 times plus 0 is 2. And then this 0, and then this 0. Now, for us to have AX1 to be equals to lambda x1, then we expect once we write 2, 0, 0, -1 times x1, which is 1, 0, then we need a number here. Remember, lambda, an eigenvalue can be 0. What cannot be 0 is the eigenvector. All the elements should be 0. Please note that one should be clear. Eigenvalue can be 0, but eigenvector cannot be 0. So then 1, 0 for this to be true. Now, this is our result. So it's like this is the same as 2, 0. You see, this 2, 0 can, if you factor out 2, then you'll have 1, 0. And this is the vector x1. So it tells us that 2, 0, 0, -1 times the vector 0, 1 is the same as 2 times the same vector 1, 0. This one is not 0. And this is a eigenvalue eigenvector equation. Ax1 equals to lambda, so we can call it lambda 1 x1. So yes, x1 equals to 1, 0 is an eigenvector of A, since it satisfies the equation A x1 equals to lambda 1 x1, and lambda 1 is 2. Actually, we have seen from here. So the eigenvalue corresponding to eigenvector 1, 0 is 2. Then for x2, so we have A x2, we have to show that the same as lambda 2 x2. So we take A 2, 0, 0, negative 1. X2 is given by 0, 1. We expect to get lambda 2 times another times the same vector 0, 1. So this will give us 2 by 0, 2 by 0 plus 0 times 1, 0 by 0 plus negative 1 times 1 to give us lambda 2, 0, 1. Now 2 by 0 plus 0 times 1 is 0. This will be negative 1 equals to lambda 2 into 0, 1. Now, for us to have 0, 1 here, we expect to factor out negative 1, 0, 1. So the same as lambda 2, 0, 1. So this indeed confirms that lambda 2 is negative 1, and hence x2 is an eigenvector of A and its corresponding eigenvalue is lambda 2, which is negative 1. So that's what we have. Part B. So we have x1, so we have to check that A x1 is equals to lambda 1 x1. So this is what we need to check. The matrix was given as B. So this is part B. So B matrix is 1, 0, 0, negative 2, 0, 1, 1, 0, 1. We multiply by x1 is given as negative 3, negative 1, 1. Should give us lambda 1 times negative 3, negative 1, 1. So this will give us 1 times minus 3 plus minus 2 times minus 1 plus 1 times 1, 0 times minus 3 plus 0 times minus 3 minus 1 plus 0 times positive 1. And then 0 times minus 3 plus 1 times minus 1 plus 1 times 1. Lambda 1 minus 3, minus 1, 1. Now, this will give us minus 3 plus 2 plus 1, 0 plus 0 plus 0, 0 plus minus 1 plus 1 equals to lambda 1 minus 3 minus 1, 1. Now, minus 3 plus 2 plus 1 is 0. 0 plus 0 plus 0 is 0. 0 plus minus 1 plus 1 is 0. So please don't get confused and say that now these are 0 eigenvector. And yet we say that we do not have an eigenvector which is 0. This is the answer for the product of the eigenvector and the matrix. So it can be 0, but the eigenvector itself is minus 3 minus 1, 1. And you see, this is the same thing as writing 0 times minus 3 minus 1, 1 equals to lambda 1 minus 3 minus 1, 1. And so this implies that lambda 1 is 0 is the eigenvalue corresponding to x1. Hence, x1 is an eigenvector for B, since it satisfies the equation, the eigenvector, eigenvalue, eigenvector equation Bx1 equals to lambda 1 x1 with lambda 1 being 0. Remember, 0 can be an eigenvalue. And then for 2, so we need to show that B times x2 given is the same as lambda 2 x2. Now, B is the matrix 1, 0, 0, minus 2, 0, 1, 1, 0, 1. So we multiply by this vector x2 was given as 1, 0, 0, and then lambda 2, 1, 0, 0. We have shown that this product can be written as linear combination of 1, 0, 0. So we'll have 1 times 1 plus minus 2 times 0 plus 1 times 0, 0 times 1 plus 0 times 0 plus 0 times 0, 0 times 1 plus 1 times 0 plus 1 times 0 equals to lambda 2, 1, 0, 0. Now you see the first row will be 1 plus 0 plus 0, 0 plus 0 plus 0, 0 plus 0 plus 0 equals to lambda 2, 1, 0, 0. So we have 1, 0, 0 equals to lambda 2, 1, 0, 0. And you see, indeed, this vector on the left-hand side can be written as linear combination of this. So i.e. 1 is the scalar 1, 0, 0 equals to lambda 2, 1, 0, 0. So it implies that lambda 2 is 1. So therefore, x2 is an eigenvector for B, since it satisfies the equation Bx2 equals to lambda 2 x2 with lambda 2 being 1. So that's how we prove that an eigenvector is a given vector is an eigenvector corresponding to a given square matrix. And that's how also we find out the eigenvalues from that computation. Thank you.